So we'll get started in a couple of minutes. So just wait. Just waiting for some people to join the session. Okay, so we'll get started. Yeah, guys, can you hear me?
Yes.
Yeah. So good evening. So this is Nilchit Datta here. I will be taking today's problem solving session on the hydraulic engineering course. So let us get started. So yeah, in today's lecture like problem solving session, I will be covering some topics from boundary layer theory, and also will be solving some problems. So first of all, like, what is boundary layer? So why this thing is important? The thing is that when a real fluid is flowing through a pipe or any flat surface or any channel, so as soon as the fluid interacts the surface of the pipe or the channel, so there will be interactions between the fluid particles and the roughness uh, of the surface. So this leads to a thing called boundary layer, that is, just near the surface the fluid velocity will be zero at the surface due to no slip condition, and the fluid velocity inside the pipe will attain the velocity of the free flowing. Like, before entering the pipe there will be some velocity, so after entering the pipe, that is the fluid will, after some distance from the surface only, the fluid will attain the free stream velocity. So for distance from the surface up to which the effect of boundary is there, so that area is called the boundary layer. So in the boundary layer we won't see that the velocity, that the fluid is directly having the velocity that it was having previously, that is just before entering the pipe or the channel, leading edge of the pipe or the channel. So there are some terms, before going into the details, like there are some terms related to the boundary layer theory. So the one thing is that so fluid velocity, that I already told, that the velocity of the fluid will be gradually entering from 0 to the free stream velocity. That is, uh, if we take a pipe like this, so it is flowing with velocity v. So just after entering the pipe, it won't, at the surface v equal to 0, at this surface also v equal to 0. So from then this effect of this surface, that is, these particles are at rest. So this will also cause shear on the other particles in just near to the particles at the boundary, and these particles will also be retarded from the motion. So this effect of this boundary will be coming to some distance from the surface, and delta this delta distance from the surface is called the boundary layer, thickness of the boundary layer. And in this between it, the velocity will be v, that is the free stream velocity. So one important thing is that inside the boundary layer there will be like large velocity gradient in the vertical direction, that is in this direction large velocity gradient. And because since the velocity is changing from 0 to free stream velocity in the center, so this in the center or to the end of boundary layer this in this area there will be a large velocity gradient from 0 to velocity v. So even if the coefficient of viscosity is might be less for some fluids, so even if the coefficient of viscosity is also less, in that case also the shear stress is like we cannot neglect the shear stress. The shear stress value will be appreciably high in those cases also in the boundary layer. So shear stress play a very important role in the boundary layer. Okay, now to get to know the thickness of the boundary layer, there are some different parameters that have been given by different scientists and people before. So the one assumption is that the thickness delta that is mentioned here, thickness delta of the boundary layer is given as the distance y from the boundary where the velocity is 0.99 of the free stream velocity. And why this is 0.99, that is also based on experiments and also based on the definitions that are given at displacement thickness and other that we will see later. And this delta distance, it is approximate thickness. It is like we are approximating it, like because we cannot directly significantly draw one line and say that okay, this is the exact thickness of the boundary layer. So we cannot draw a thin boundary like that. So it is just approximately, slightly like approximate to some small ratio, but yeah, it is well approximated. So to get as like so to get properly estimate the value of boundary layer thickness, there are three definitions that are introduced. One is the displacement thickness, that is given by delta star. The second is the momentum thickness, that is given by theta, and the third is the energy thickness. And all the three definitions will be based on, all the three parameters are based on three different definitions to account for the thickness of the boundary layer. Okay, so first of all is the parameter delta star, that is displacement thickness. So what exactly is displacement thickness? So the displacement thickness is like the distance from which the boundary, by which the boundary surface is displaced, so that the actual discharge through the displaced boundary is equal to same as the ideal fluid past that boundary. Okay, sorry. It is, so the actual discharge equal to the same as that of ideal fluid past that displaced boundary. So how do we define this delta star? So to define delta star, first of all we should go to a definition, that is what it says, that the discharge the discharge through actual discharge is equal to is same as that of ideal fluid past that boundary. So if we take the free stream velocity as value of as velocity v, and the delta star is the displacement thickness, so if we take the discharge will be v into delta star. So through this, if we take one surface, this is surface, and we take, suppose this is delta star. So a discharge through delta star should be equal to actual velocity. So the actual velocity is actual discharge. So the actual discharge is, so in this region the velocity will be given as free stream velocity minus of small v. Sorry, not in this region, that is just outside. It is given as capital V minus small v, where v is the velocity in boundary layer. So that actual discharge is given as 0 to delta v minus v of dy. So based on this definition, we get delta star, which is equal to 0 to delta 1 minus small v by capital V of dy. So similarly, there is another definition. This is called the momentum thickness of a boundary layer based on the definition of momentum. So it is a distance from the boundary such that the momentum flux corresponding to the mainstream velocity v through the distance theta is equal to loss in momentum due to boundary layer formation. So the loss in momentum will be, so this is the loss in momentum due to boundary layer formation, that is rho into v minus v into small v into dy, and we are integrating because the v is changing over a distance y, and momentum flux in the region theta is rho v square into theta. So if we rearrange the terms, we will get the momentum thickness as theta equal to v by v 1 minus v by v into dy from 0 to infinity, or you can say 0 to delta. And third definition is the energy based on the energy thickness. So that delta E is given a distance from the actual boundary such that the energy flux through the region delta E is equal to loss in energy due to boundary layer formation. So delta E, this also will be coming from the definition of energy. So half rho v cube delta E, this is the energy of flow in the region given by height delta E, and the loss in energy due to formation of boundary layer will be half rho. We are taking rho as constant, that's incompressible, from 0 to delta. It will be v square minus small v square into v du. So from, if you rearrange the terms, you will get the value of delta E. This is how we obtain the three definitions of boundary layer. Okay. So based on these definitions, there are some questions. So the first question is the momentum thickness of a boundary layer is, so we already discussed, the momentum thickness is given by v by v into 1 minus v by v into dy. So it is option A. Okay, now second question is, the displacement thickness is a layer in which there is a loss of energy is minimum. No. The layer which represents reduction is momentum caused by boundary layer. No. So the thickness up to which the velocity approaches 99% of free stream velocity. No, because this is the actual definition of boundary layer. So the distance measured perpendicular to the boundary by which the free stream is displaced on account of formation of boundary layer. So the correct option is option D. And the next question is, the boundary layer exists in which of the following? So in case of ideal fluid, there is no viscosity. So if there is no viscosity or there is no shear between the layers, then in that case there will be no boundary layer formation. So the boundary layer formation will be there for flow of real fluids. So it is answer is A. Okay, let us now solve a numerical. What is the energy thickness for a boundary layer with velocity distribution u by u equal to y by delta? So the energy thickness is given by delta E division of 0 to delta small u. We can write u by u or v by v, both are same, so 1 minus square by dy. So let us replace u by u by y by delta. Now 0 to delta, we'll do the separation of terms y. dy minus of 0 to delta y square by delta square into dy. So it will be 1 by delta into 0 to delta y cube by 3. So it is delta by 2 minus of delta by 3. So it is delta by 6. Sorry, this is my it is y cube by delta cube. So after for 4 by 4, so it will be delta by 2 minus delta by 4. So the answer is delta by 4. So it's delta by 4. Okay, there is one more question. So what does it say? So it says the velocity distribution in a boundary layer is given by v by v equal 3 by 2 eta minus of half eta square, in which eta equal to y by delta. So we have to compute delta star by delta and theta by delta. Okay, let's start. So eta is given as y by delta. So what will be d eta? D eta equals to dy by delta. Okay, so first let us compute delta star. Delta star equals to 0 to delta one minus v by v dy. So let us replace the value of v by v from the equation given above. 0 to delta 1 minus 3 by 2 eta minus of eta square by 2 dy. We will replace dy as delta into d eta, eta into d. So it will be delta into d eta from here. So delta you can take outside and we can integrate the terms inside. What does it come? So delta star by delta okay. So one thing, when you are changing the scale, if you are changing the y to delta, so this scale will also change, the upper limit will also change. Since for if y equal to delta, eta equals to y by delta equal to 1. So here the upper boundary condition is from 0 to 1. So it will be eta minus 3 by 2 eta square by 2 minus of half eta cube by 3, 0 to 1. 1 minus of 3 by 4 minus of 1 by 6. I think it is 5 by 12. So this is for displacement thickness. The second part we have to calculate for theta. It is the momentum thickness. So yeah, let me add on. Now we know for momentum thickness it is given as theta equals to integration of 0 to delta v by v 1 minus of du. Now we will replace the value of v by v and dy as eta dy. So this will also change the limit. Limit will be 0 to 1. v by v is 1 3 by 2 eta minus of eta square by 2, and this is 1 minus 3 by 2 eta minus of eta square by 2 into delta d eta. So if we can take delta out and take it to denominator, so theta by delta is given as 0 to 1. So we'll multiply and get all the terms. So 3 by 2 eta minus of simplify all the terms. So after integration we will get 3 by 2 into eta squared by 2 minus 3 by 4 eta to the power 4 by 4 minus of eta cube by 6 3 by 4 eta to the power 4 by 4 minus of eta to the power 5 by 4 into 1. So let us substitute the values. 3 by 4 eta equal to 1. For eta equal to 0, it means all the terms will be 0. So for we have to get only for 12. So 3 by 16 minus of 1 by 6. So if we can take the denominator, and it will be coming as 120, 19 by 120. So this is how you will get the momentum thickness and the ratio of momentum thickness to the actual boundary area. So that is the reason. So since cannot directly define the exact boundary layer, so we go with approximate definitions of momentum thickness and displacement thickness. Okay, so next we will see like how the boundary layer forms if we consider a flat plate, how the boundary layer forms, what are the equations of motion and equations that are valid inside the boundary layer. We will see through this. So this is the schematic for a boundary layer. So as soon as flow enters the flat plate, this is the leading edge. Okay, so this is the leading edge. As soon as it strikes the leading edge, the boundary will have impact on the boundary on the flow, and the boundary layer will be formed. Now initially the laminar boundary layer will be formed, and there is a transition region, and thirdly there will be a turbulent boundary layer with a laminar sublayer. So I will go into definitions of this laminar, turbulent and transition boundary layers. First of all, like let us see what are the factors like that actually affects the thickness of the boundary layer. So the factors affecting thickness of boundary layer. So the first factor that is evident here is the distance from the boundary leading edge. So as soon as the flow enters, the effect of the boundary is like just it will just be coming to the flow, like it is just been impacting the flow. But as you move just slightly away from the leading edge, the effect of the you can see suppose we have moved a distance L from the leading edge. Suppose we have moved till here. Suppose so this whole distance, this whole rough boundary, whole particles in the rough boundary will be impacting the flow, and since the particles just near the surface will be at rest, so all these particles will be due to no slip conditions. So all these particles will be impacting the flow, the overall flow, and it will due to the shear that will be in a river, like shear force that will be applying on each of the layers. So as you move away from the leading edge, the effect of boundary will be more noticed in the flow. So the first factor is distance from the leading edge. The second factor that affects the and so if the distance is more, the height of the boundary layer is more. But after a particular distance, the boundary layer will be fixed, and it will merge with the free stream velocity. The second factor is the velocity of flow. If a fluid is flowing with very high velocity, so in that case the fluid velocity, it can overcome the effect of the boundary layer, that the effect of the shear force that is impacting to retard the flow acceleration or the flow velocity. So if the velocity is high, then the height of the boundary layer will also be low. So velocity of the flow. So if V increases, delta decreases. And the third thing that is that will impact the height of the boundary layer is the pressure gradient, that is delta P by delta X in the direction of the. So if we take for uniform velocity, like if the velocity is not accelerating, then for uniform flow, del P by del X equal to 0, and So in that case, the pressure gradient won't be impacting the boundary layer depth height if the in case of uniform flow. But if we take a converging flow where del P by del X is less than 0, that is flow is due to a pressure gradient. So if the pressure is high, the flow is taking from a region of high pressure to a low pressure, that is delta P by delta X is less than 0. In that case, the boundary layer thickness will be retarded by the flow pressure gradient, because since the pressure gradient is high, it will also increase the velocity of the flow, and in that case the boundary layer thickness will also be less. So growth is retarded. So now we have seen what are the factors that impact the boundary layer. Now let us see come to the definitions of the three main boundary layers. One is the laminar boundary layer, then turbulent boundary layer, and the laminar sublayer. So whether the flow is turbulent or laminar, in either case the laminar boundary layer will be forming from the leading edge to some distance. So to from a leading edge to some distance, the laminar boundary layer will be formed. So this laminar boundary layer will form irrespective of the flow is laminar or turbulent, and the velocity distribution in the laminar boundary layer is parabolic, that is V minus V directed to equation to delta minus Y whole square. Secondly, there is the turbulent boundary layer. So and there is a transition boundary layer. So in transition region, the boundary layer will be moving from from laminar to turbulent. So it is very difficult to define. So even in a transition region also, we can say the velocity profile is mostly parabolic only. But when we go to a turbulent boundary layer, there is a rapid increase in the boundary layer thickness. So the flow in the turbulent boundary layer, the flow in the boundary layer will be turbulent, and the velocity distribution generally follows the power law, which is also called the 1/7th law. This we have seen in last class also. And V is proportional to y to the power 1/7, or it also can also follow the logarithmic law. Now one more thing that is very important is the laminar sublayer. So in the turbulent boundary layer, and there is, if the surface is sufficiently smooth, in that case there will be for a region there for a very small height, there a laminar sublayer will be formed in which the velocity distribution will be parabolic. But we assume that since the thickness of the layer is extremely small, so we can assume that the velocity can be assumed to be linearly varying. So this is the assumption, but in reality the velocity distribution is parabolic. So this thin laminar sublayer will be formed when the surface is hydrodynamically smooth. If the surface is hydrodynamically rough, in that case this laminar sublayer won't be formed. So I think these things are defined in the course. Now the thing is, how do we define the laminar layer or turbulent layer? How do you distinguish that, okay, if the boundary layer here it is the flow is laminar, or in this part of boundary layer the flow is turbulent? So this is based on the Reynolds number, where the Reynolds number is given as rho v into x by mu, where v is the free stream velocity, rho is the density of the flow, x is the distance from the leading edge, and mu is the viscosity of the fluid. So if it is less than 6 into 10 to the power 5, then it is say that the flow is laminar or in transition region. If it is greater than 6 into 10 to the power 5, it is, we call that the flow is the laminar boundary layer is turbulent. I think there is also one definition. Just let me check. So this is displacement thickness. Yeah, so the correct definition that is given based on the textbooks is Rex less than equal to 5 into 10 to the power 5 is given as laminar boundary layer, and if the Reynolds number of the Reynolds number of the flow is given as greater than 5 into 10 to the power 5, the boundary layer moves from laminar to transition, and if it is greater than 6 into 10 to the power 5, we call it as turbulent. Okay, so now let us see through the equations of a boundary layer. So what are the equations that are valid in a boundary layer? So the first thing is we are considering the flow to be incompressible. If the flow is considered incompressible, then the continuity equation is given as, and the flow is two-dimensional, 2D. We are not going to 3D flow because of for simplicity reasons. So in case of incompressible flow, the continuity equation is given as del u by del x plus del v by del y equal to 0. Now coming to the equations of motion, the first thing is the net force in x direction. So to go into the equations of motion in x direction, first you should know that the total force in x should be balanced by the So what is the total force in x direction? So the force in the boundary layer is mainly due to the shear between the layers. So small layers in shear between different layers in the boundary layer. So the shear, if you take a small element that define for defining the shear stress. So at the bottom we have the shear stress tau, and at the top the shear stress is tau plus delta over a distance of delta y. So the rate of change of tau is given as del tau by del y, since we have the change of delta tau by delta y, and if we take this change in shear stress per unit mass, so it will be a 1 by delta by del y divided by rho into delta x into delta y. So we are taking per unit mass only, since the momentum equations are also given in terms of everything is all the forces are per unit mass. And secondly, so now if we know delta by del y and we know from Newton's law of viscosity, we can write that this 1 by rho delta by del y, it can be written as mu by rho del square u by del y square, and mu by rho is given as a kinematic viscosity, so it is nu del square u by del y square. It's a net force in x direction. So if we, this is the net so the equations of motion in x will be this also comes from, you can also derive it from a Navier-Stokes equation, but if we directly write in terms of what are the important components, one is the acceleration, and also we have considered in this laminar sublet, we have considered flow to be steady. So the equations that come into the equations that are important are u in the x direction is u into del u by del x plus v into del u by del a. This comes from the convection part of the Navier-Stokes equation, or from the simple momentum equation, and this is balanced by the two forces. One is the shear versus the force due to pressure gradient, and due to the shear. So these two forces are being applied in the x direction. One is shear stress acting to retard the flow, and pressure gradient is acting to accelerate the flow. So these two forces are acting in opposite directions, and the net force, net change in momentum, rate of change in momentum is given balanced by these two forces. Similarly, in the y direction, there is no change in pressure, that is, there is no change in not much change in shear stress. There is change in shear stress, but in the y direction the rate of change of velocity, that is vertical velocity, is extremely low. It is like near to 0. So del square v by del y square will almost tend to 0, and also del v by del x and del v by del y is also will almost tend to 0 in terms of the pressure compared to the pressure gradient. So if we apply order of magnitude studies, then these terms will tend to 0, is neglected. So the only remaining term is 1 by rho del p by del y equals to 0. So these three equations, they form the basis of the boundary layer but this PD, these partial differential equations are very difficult to solve directly and solve analytically in case of a boundary layer. So difficult to solve analytically. So the Vaughan and Karman, they are two scientists who developed a method to solve a boundary layer equations. It is called the Vaughan-Karman momentum integral equation of boundary layer. So they integrated these equations and tried to develop a method, and they found that the rate of that d by dx of v square theta plus d by dx of v delta square equal to tau naught by rho, where tau naught by rho is given as shear velocity. is given as shear velocity square. So here v is the free stream velocity, theta is the momentum thickness, and delta star is the displacement thickness. So with a flat plate with zero incidence, that we consider del p by del x equal to 0, we can say that dv by dx is also equal to 0. So for that case, we can assume that from this equation we can get that tau naught by rho equal to d by dx of v square theta. Since dv by dx equal to 0, so tau naught by rho v square equal to d theta by dx. This is a very important equation, so this can be used to solve or even one second. So this is how the momentum integral equation is at the boundary layer. It is forms as a basis of like approximate method for solving the boundary layer problems. And in this method is applicable to both laminar as well as turbulent boundary layer. No assumptions has been made regarding laminar or turbulent, and it should be noted for a flat, that is the equation is this to tau naught by rho v square equal to d theta by dx if we take flat plate with zero incidence, that is dp by delta p by del x equal to 0. Now comes what are the equations that we get for a laminar boundary layer. So in case of a laminar boundary layer, we will get the equations of inertial and viscous forces are of same order of magnitude. The first thing that we should note here in the laminar boundary layer is that the viscous forces are quite significant, and they are all the same order of magnitude as the inertial forces. So from the momentum integral equation, we get that the inertial forces are of the order of rho v square by x. So this rho v square by x, and the viscous forces are order of mu of delta by del y. So delta by del y again is del by del y of mu dv by dy. So we will get mu into v by delta square. So if these are of the same order of magnitude, then you can equate this using a constant, arbitrary constant k dash, or it is a proportionality constant k dash, and from this we obtain the value of delta as delta equal to delta by x equal to k by root re x, or delta equal to k into x nu by p. So now Blasius, he did some experiments based for boundary layer, and based on experimental results he obtained the equation that delta is approximately 5 into x by. So if we take at a distance x from the leading edge, so the boundary layer thickness at a distance x from the leading edge is given as 5 into x by root rex. So this is given by Blasius, and for the boundary layer thickness based on some experiments that he performed. Now we can also get some equation for the shear stress. So if we can consider the tau naught as shear stress at a boundary, and tau naught is given as mu into del v by del y. So it is given as mu into v by delta. Del v by del y equal to, you can write as the order of v by delta. So what will happen to the equation? So if we, from the momentum integral equation, we will get tau into tau naught by rho v square, we will get as constant divided by root re x. and it is constant. Second. Okay, sorry for the interruption. Okay, so based on experiments, this constant is obtained as 0.664 by Blasius. So the tau naught, the shear stress at the boundary, and the rho momentum are related as rho 0.664 by root Rex. Now from the exact solutions of the boundary layer equations by Blasius, so these equations are obtained analytically. He obtained that delta star, that is displacement thickness, is obtained as 1.729 by root Rex into x, and for theta by x he obtained as 0.664 by root Rex. And secondly, this if we consider a linear velocity distribution in the flow, the velocity is linear. In that case, we can solve the equations in the simple solving on the equations becomes quite simple, and we will get the displacement thickness is 1.732 by root Rex, and this momentum thickness is 0.5774 x by root Rex. Thus, you can see that even for a linear velocity distributions, the displacement thickness and the momentum thickness are approximately matching the analytical solutions that has been obtained by Blasius obtained by Blasius. Now coming to turbulent boundary layer. So first assumption in turbulent boundary layer is that the velocity follows a logarithmic law, or it can also follow a power law. So v is equal to log y or we can assume that v is equal to y by delta to the power n, where n equal to 1 by 7. So for turbulent boundary layer, so the equation of the boundary is obtained as delta by x equal to 0.376 by r e x to the power 1 by 5. Now we have now we can see that in the laminar boundary layer the delta, that is the thickness of the boundary layer, it varies as a square root of x, that is x by root r e x. If we take root, r x equal to rho v x by mu. So x by root x will come as equal to root x. So it is varies as square root of x. But in case of turbulent boundary layer, if we substitute the value or the formula for Reynolds number, then we can get delta is following x by x to the power 1 by 5, x to the power 4 by 5. Thus the boundary layer thickness is increasing quite rapidly in case of a turbulent boundary layer. Now coming to the last parameter, that is the laminar sublayer. Laminar sublayer, we have assumed that the velocity distribution is almost linear. So the equation for the height thickness of a laminar sublayer is given as 11.6 v by v star, where v star is the tau naught by rho, or also called as shear velocity. Now there are two types of boundary that are often encountered in fluid mechanics, and one is the hydrodynamically smooth boundary and the other is the hydrodynamically rough boundary. So the hydrodynamically smooth boundary is identified by the parameter, by the value of the dimensionless roughness parameter, and this roughness parameter is given as v star into ks by nu, where ks is the average height of roughness projections. And if we consider hydrodynamically rough boundary, then if the roughness parameter, the value should be greater than 70. Again here ks is the height of the roughness projections. Okay, so let us solve one or two questions. So in a laminar boundary layer, the velocity distribution is assumed to be given in usual as u by v equal to y by 7 delta to the 1 by 7, which are the following is the correct expression for the displacement thickness delta star of the boundary layer. The delta star is given as 0 to delta 1 minus v by v, so or also called u by u. So we will replace 1 minus to the power 1 by 7 of dy. So it will be delta minus of 1 by delta to the power 1 by 7 and integration of y to the power 1 by 7 equal to y to the power of 1 by 7 plus 1 equal to 8 by 7 divided by 8 by 7 to delta. So delta minus of delta to the power 8 by 7 minus 1 by 7 equal to 1 delta by 7 by 8 delta by 8. Okay, let's come to the next question. Here it is. Okay, a smooth plate 2 meter wide. So let us have a schematic. 2 meter wide. We are not here. It is not in our consideration for boundary layer theory, but just for schematic purposes, I will show that. So how the flow parameter, how is the flow is taking place, and 2.5 meter long is towed with oil and a velocity of 1.5 meter per second. So oil is coming at a velocity of 1.5 meter per second. So free stream velocity is 1.5 meter per second along the length. Find the thickness of the boundary layer at the trailing edge of the plate. So trailing edge means at this point, this is the leading edge, this is the trailing edge. So if we take this as the boundary layer, so we have to say first, to get the height of the boundary layer, we have to first identify if it's a laminar boundary layer or a turbulent, or it is shifting from laminar to turbulent in between. So to first get that, we need to identify the Reynolds number. So Rex equal to rho Vx by mu, and kinematic viscosity is given as 10 to the power minus 4 meters square per second. So mu by rho equals to 10 to the power minus 4 square per second. So we know V is 1.5, X if we take 2.5, and mu by rho is 10 to the power minus 4. So we get a value of 37500. This is less than 5 into 10 to the power 5. So this is the laminar boundary layer. So now in case of laminar boundary layer, we can estimate the height of the boundary layer at a distance x as 5 into x by root Rex. This is given by Blasius, so it is 5 into 2.5 divided by under root of, and this will come roughly as 0.0645 meters. Correct answer is 0.0645 meter. Okay, now again one question on energy thickness. So energy thickness of the boundary layer by distribution U by U equal to Y by delta. So energy thickness is again given as delta minus U square by U square into dy. So it is 1 by delta into y square by 2, 0 to delta minus 1 by delta cube and y cube by y to the power 4 by 4. So if we delta E is delta by 4. Simple numerical. So now we will move on to A turbulent boundary layer occurs over a flat plate practically right from the leading edge. Okay, so in what case condition is this possible? It is possible for the surface to be hydrodynamically rough upstream and yet hydrodynamically smooth downstream. So even if we take a hydrodynamically rough surface, even if that in the laminar first initially a laminar boundary layer will be forming, so that is hydrodynamically rough or smooth won't be a factor here. Secondly, it is possible for a surface to be hydrodynamically smooth upstream and yet hydrodynamically rough in that if this won't be true anyways, since if it is hydrodynamically smooth upstream also, then initially a laminar boundary layer will be formed and then a turbulent boundary layer. And the third case is if the flow is rough on the upstream, it has to be rough on the downstream also. This can be true. So if the flow is rough and also flow is rough on both downstream as well as upstream, then in that case a turbulent boundary layer can be formed directly at the incidence point. A laminar sublayer exists. This will exist in all turbulent boundary layers. In every turbulent boundary layers, then a laminar sublayer will exist always. Sorry, it's not always. If case of hydrodynamically smooth, if the surface is smooth, then below turbulent boundary layer there will be a laminar sublayer. Now there is one more question: the aging of pipes implies which of the following? So if a pipe is aging, so the roughness in the pipe will be increasing due to corrosion and other factors. So in that case, there will be an increase in absolute roughness linearly with time, and hence the friction factor. It can be linear, it can be linear, but since linear is the only option given in this numerical in this question, so we'll go with option B only. Okay, so the velocity profile of a turbulent boundary layer is given by ux by u equal to y by delta 1/7 for y less than equal to delta. The shape factor for turbulent boundary layer shall be. So now the shape factor is given as y star by delta equals to m y star by theta, the displacement thickness by momentum thickness, and this ratio is given as m plus 2 by m, where m is the power of velocity distribution. So y star by theta will be equal to 1/7 plus 2 sorry, m is not 1/7, m is 7, 1 by power. To 9/7. So the shape factor is given as 9/7. Now let us come to the phenomenon called boundary layer separation. So what is boundary layer separation? So if the pressure gradient is adverse pressure gradient, in that case what happens, like del P by del X is greater than 0. So the flow is extremely retarded, that is the flow cannot take from low pressure to high pressure. So high flow always takes from high pressure to low pressure if the pressure gradient is adverse. In that case, the flow is extremely retarded, and also the shear stress that is already retarding the flow in the boundary layer will be impacting retard the flow. In such a case, the boundary layer on the surface will be moving in sideways direction. That is, it will, if the plate is like this, the boundary layer, if it was at this position, it will move to this position. So this is called the boundary layer separations. So this boundary layer is separating from the mainstream velocity, and this is leading to phenomenon called boundary layer separation. And the fluid in the boundary will all be coming almost to rest, and the boundary layer as a whole will be shifting. So this is one phenomenon shown for a curved plate. We can see at initially the del v by del y is greater than 0. At the center here, del v by del y is equal to 0, and from here, this point, the del v by del y is less than 0. So the flow is trying to reverse. That is, the flow will try to take place in the opposite direction, and this is causing a shift in the boundary layer, and due to adverse pressure gradient, and del v by del y depends on the del v by del x. So the streamline also separates, and this will lead to a boundary layer separation. So this is the condition how we can so the separation point is identified by this condition. It is du by dy equal to 0. If du by dy is less than 0, we can say that the flow is separated. If the du by del y is greater than 0, it is on the range, it is not in the range of separation. So now how can we prevent a boundary layer separation? Separation of the boundary can be prevented by three main methods. First is slotted wing. So if we can create a small inlet so that the flow from the mainstream can enter the boundary layer, and it can accelerate the boundary layer. So in that case, we can prevent the boundary layer separation. So this is one method of preventing boundary layer separation. The second method is if we take the flow over a curved surface. If we take a spherical ring or a ring or a wire, so if the flow is taking place over the curved surface of the ring or the sphere, then the flow will be accelerated, and and as will be, since the spherical ring will also be moving with the flow, so the particles on the surface of the flow of the sphere or the ring will also be moving with the flow. So in that case, the boundary layer won't be coming to rest. So this will also create the prevent separation of boundary layer. But one thing to mind here is, like, as we come to the bottom part, in this part we can see that the flow, the sphere or a ring has opposite direction of is moving in direction opposite to the flow. So in this case, in the bottom part of the tire trip wire ring or the sphere, there can be a boundary layer separation. And the other option is, like, we can also inject fluid into the boundary layer. We can make a small divergence and inject fluid into the boundary layer. So all these three methods are used for preventing boundary layer separation. So the last question is, like, which of the following flows Blasius equation is used? So Blasius equation is given by 5x by root RE. So that is used for turbulent flow in pipes for Reynolds number less than 10 to the power 5. And this is the condition for which the Blasius equation was derived. So let us solve one quick numerical. It is given that a smooth two-dimensional plate exposed to a wind velocity of 100 km/h. If laminar boundary layer exists to Rex of 3 into 10 to the power 5, then find the maximum distance up to which a laminar boundary layer persists. X and also find the maximum thickness of the boundary layer. So nu is given as 1.49 into 10 to the power of -5 meter square per second. So let us solve this numerical. So what is given? So first it is given that this free stream velocity is 100 km/h. So let us convert this to meter per second. 100 into 1000 by 100 meter per second. So it will come as 1000 by 36. It will be 27.78 meter per second. Now Reynolds number is given as Rex is equal to Vx by mu. Now we have, it is given that it follows up to a maximum distance of, what is the maximum distance up to which the laminar boundary layer is valid. So we have Reynolds number is given as 3 into 10 to the power 5. V is 27.78 into x divided by mu. Mu is 1.49 into -5. So from this we obtain x equal to 0.161 meter. Now we obtained x. So if we are considering only laminar flow, then delta is given as 5x by root Re. So 5 into 0.161, this is from Blasius equation, under root 3 into 10 to the power 5. If we solve this, we will get 1.47 into 10 to the power -3 meter, to 1.47 mm. So you can see how thin is the boundary layer even at a distance of 0.16 meter, it is 16 centimeter. So this is mostly all about boundary layer theory. There nothing much to cover here. If you have any doubts, you can ask me. I will wait for some time. Okay, let us one. So only one more question from the assignment. Issue of delta star theta for now we have know that delta for a linear value distribution. I can say that this u by v is y by delta, that is velocity is linearly varying at y. So let us calculate delta star. Delta by 2. So now theta equals to 0 to delta u are v1 minus. So if I solve this, by 2 minus delta by 3 delta by 6. So delta square delta star by theta can get as equal to 3. The correct answer is 3. So if there are any other doubts, you can ask me, or else you can. I will wait for some time, else we will get completed. Okay, so I will end today's session. If there are no doubts and nothing to ask from your side. So it was a pretty easy topic. We'll see again in the next week. Thank you. I will hope to see you again in the next week with the new topics, and we'll solve some brainstorming problems. So thank you for joining and watching my session. So please follow my YouTube channel. You can see the link for all the videos in that channel.